So quickly, we're just going through removing your OH. So you're going to turn your thing into a halide, into a haloalkane, and you're going to do that with your phosphorus halides rather than your hydrogen halides, is what we did in the halogen alkanes. So one method is using PCl3, giving you phosphorus acid, which is different to phosphoric acid, and the fact that this is not an OH group, this is just an O group. So that's one method of making it, and you're resulting in your haloalkane over here. And if you use PCl5, well, first the conditions, we have room temperature, and it produces clouds of hydrogen chloride gas. It's not great, but it is used for a test for OH groups. Now, if you want to show that something was an alcohol, as in it contained an OH group, then you have to eliminate first all the other things that could react with phosphorus chloride. Okay, for example, carboxylic acids could react because it contains the COH group. C, your phosphorus V chloride is going to be the thing that's used to test for OH groups. So since COH also contains an OH, since water also contains OH, then we have to remove those. If you have a neutral liquid not contaminated with water and get a violent reaction producing steamy films of hydrogen chloride when you add phosphorus V chloride, then you have an alcohol group present. Okay? Practically just saying that if you're sure that it's neutral, as in it doesn't have any acids, as in carboxylic acids, and also that it's pure, that it's pure without any water, and also you get steamy fumes of hydrogen chloride gas, then only when you react it, then you have your alcohol present, and most likely that's going to be alcohol present in here, and as a result, so since you can have hydrochloric gas, it's going to be like this. This is going to be a POCl3, which is going to be, I'm not sure what that is called, but then you also have your haloalkane. There's some side reactions using POCl3, and you're reacting with the alcohol. So if you have more alcohol, so this reacts with this. So do we talk about that? I don't think so. So now you have your other reactions involving phosphorus halides. Of course, we're always starting with PCl5, which is a phosphorus halide, and over there in the previous one, PCl3. Now, for PCl5, for the other ones we're seeing, instead of using phosphorus 3 bromide or iodide, what they mean by that is, for the previous ones, we used chloride alongside with your phosphorus. Now, if you wanted to do it with the iodide or bromide as you go down the group, then you would have to use a different one. Instead of phosphorus 3 or phosphorus V, we would have to use a mixture of red phosphorus and either bromine or iodine, depending on which one you wanted to replace the alcohol with. This is similar to what we did before in haloalkanes. Phosphorus first reacts with bromine and iodine to give the halide, the phosphorus halide, and the phosphorus halide then reacts with the alcohol to produce the haloalkane and the phosphorus acid. Now if you react alcohol with sulfur dichloride oxide, this is going to be a weird reaction, but let's see. So sulfur dichloride oxide, which is thionyl chloride, has the formula SOCl2. So as we can see, it contains the Cl2, which is going to be our halide. It contains our sulfur, could be our oxidizing agent. Now, traditionally the formula is written as shown, despite the fact that the modern name writes the chlorine before the oxygen in alphabetical order. The sulfur dichloride oxide reacts with alcohols at room temperature to produce chloralkane. So here is going to be your one of your things, sulfur dioxide and your hydrogen chloride are given off. So we have two gases this time. We have sulfur dioxide and hydrogen chloride. In the previous one, we had HCl also given off, and this one we also have HCl given off, as it contains the Cl. However, one of the Cl's in this dichloride is going to be inside the alkane, and you have your SO2 and your HCl. This is really useful for the fact that it is either the reaction has a big advantage over the use of either phosphorus chlorides is that the two other products of the reaction are both gases. This means that they separate themselves from the reaction mixture. So we have to distill the other ones, or filter, because in the previous ones we see that this is always being mixed as a mixture between these two. So now we're actually seeing that since both of these are gases and this is a liquid or whatnot, then these will go and separate, and this will separate as well. And also these are two different gases, and these aren't a mixture of gases, these also separate. You can separate them using the distillation or whatever. Now if you move on, you have oxidation of alcohols. So we're seeing acidified sodium, potassium, then dichromate solution. So we're using two metals here. I think in our syllabus we use one or the other, I don't remember quite well. Now this reaction is used to make aldehydes, ketones, carboxylic acids, and a way of distinguishing between primary till tertiary alcohols. Okay, so this is a lot of new terms being used here. Aldehydes, ketones, and carboxylic acids. Carboxylic acids is the only old one. At this point, let's read this page unless you're confident you know what these are. So it'll constantly refer to aldehydes and ketones. Follow this link if you don't know what those are. So 1 second, guys. This is going to be a fairly long topic, but alhamdulillah, there's no side links here, so this is going to be a one-off thing. So if you go on, just talk about aldehydes and ketones before we start, right? So yeah, what are aldehydes and ketones? How bonding affects their reactivity, considers physical properties such as solubility and boiling point. If you've noticed already, these are the only things that we're actually looking at in organic chemistry in terms of physical properties. And also, so we usually look at things. We look at reactivity, we look at solubility, we look at boiling point. These are the main three things, okay? And these three things are usually interlinked. Maybe perhaps solubility is not interlinked, but boiling point and reactivity are usually inverse, and they depend on the bonding, which is usually the IMF. Okay, so yeah, reactions of the aldehydes and ketones are described on separate pages. We don't need to know that. We just need to know how they're formed, which is probably going to be majority of the reactions of aldehydes and ketones. So here we go. Now these are carbonyl compounds, and they contain a carbonyl group, which is a carbon oxygen double bond. So both of these are going to be alkenes kind of thing. In the fact that not really. Alkenes is when you have double bond between two alkyl groups. Here we have a carbonyl where you have carbon and oxygen, okay, double bond. They are simple in the sense that they don't have other reactive compounds like OH or Cl. It's only O and C, okay, and they're not attached, so they don't have like actually reactive elements like OH and Cl. Those are reactive because they have, Cl is electronegative and O has a double bond. Has lone pair. So in carboxylic acid you have COOH. So although it contains a double bond, it also contains two O's, which makes it quite reactive. Now in aldehydes, the carbonyl group has a hydrogen atom attached to it with either the second hydrogen atom, or more commonly a hydrocarbon group, which might be an alkyl group forming one might be an alkyl group or one containing a benzene ring. So let's just repeat that. It has a carbonyl group, which is a C double bond O, which has a hydrogen bond attached to it. So C double bond group with a hydrogen with a hydrogen attached to it, with either a second hydrogen atom, which is basically just COOH plus perhaps another H attached to it, or you have another hydrocarbon group, which might be an alkyl group or one containing a benzene ring. So this could either be another CH3, so this could be another alkane group, or alkyl, whatever you want to call it. This could be another alkyl group, which will lead on, or it can be part of a benzene ring in terms of, like, it'll start forming a benzene ring like this, kind of like that. Okay, that's what I'm understanding by that. Anyways, we shall ignore the benzene rings. There is no significant reason for this. It's just if you're fairly new, then you might not come across compounds with benzene rings. I'm just trying to avoid it. Yeah, okay, fine. So here we have, it'll be anal. Okay, so methanol, ethanol, propanol, 2-methylbutanol. Okay, and they're just saying that it's 2-methylbutanol. So the first C is counted, second C is involved in the 2-methyl, the 1 C is over here. So that's great. Notice that these all have exactly the same end. All that differs is the complexity. Yep. So examples of some ketones here. We're seeing that the carbonyl group has 2 carbon. So now we're looking at ketones. What were we looking at? No, yeah, we were looking at aldehydes. So we're already looking at ketones already. This is 2 hydrocarbon groups attached. Okay, 2 1 C double bond O. So you need to have 2 attached. In the other case, we could have a double bond O attached to an H, and the other one could be an H or it could be a CH3. Okay, or an alkyl group. This time it needs to be connected to 2 hydrocarbon groups. Again, this could be oh, whoops, never mind. Oh, no, never mind. Yeah, I was right. So this could be 2 alkyl groups or one containing benzene rings. Okay, so as in this can be just one form of one benzene thing, or maybe I'm wrong. I don't know. So I don't know what's so different about a benzene ring. Just keep it in mind, I suppose. We'll okay, notice that ketones never have a hydrogen atom attached to the carbonyl group. Yep, because if it did, then it would turn into an aldehyde. Now propanol is okay. So we have with the functional group name is known. So we're having propanone, butanone, pentane 3-on. So we see that it's pentane 3-on. So we start from here. So we go 1, 2, 3, 4, 5. So this is going to be your pent, and it's starting at your 3. If you start at 1, 2, 3, 4, 5, would have been the exact same thing. Over here is 1, 2, 3, 4. Why is this not called butane 2-on? Is because no idea actually. What is going on here? Why is this considered 1, 2, 3? Is that an error? Propanone is usually written as this. Notice the need for numbering longer ketones in pentanone. Oh wait, what? It needs numbering only in longer ketones. Look over here, it's 1, 2, 3. And you didn't have to mention that it's in 2. But over there you need to mention it's 3. Notice the need for numbering in longer ketones. In pentanone, the carbonyl group could be in the middle of the chain or next to the end, either giving 3-pentanone or pentane 2-on. Pentane 3-on or pentane 2-on. So if this was over here instead, it would produce the same product. However, if this was here, then it would be produced something different. And if it was here, it would be produced something different. Okay, that's why it's not. Over here, if it was here, then you have CH3, CH3, C double bond O, which would not be possible because it's bonded to only 3 things. So it would be probably bonded to an H, which would make it an aldehyde. this one needs to be bonded to two different alkyl groups, which means that it needs to be in between. It needs to be in between, aka it needs to be a primary or secondary. Do you understand? In fact, it needs to be a secondary always, because if it was well, perhaps not. Does it need to be if it's bonded to? Are we talking about this carbon group, or are we talking about the carbon group that it's attached to? I'm not exactly sure, but I'm pretty sure it's always going to be secondary. So now we talk about your bonding reactivity, and then we're going to be talking about your boiling points and solubility. So bonding in a carbonyl group, so we're talking about your aldehydes, right? Your C double bond O, and well, not really. We're just talking about the C double bond O and both. So oxygen is far more electronegative than carbon, and so okay, yes, it's going to be far more electronegative. Although there's a double bond which is given to the bond, it's still going to be far more electronegative because there is a tendency to pull the electrons in a carbon oxygen bond towards itself. One of the pairs of electrons, one of the two pairs, because you have one pair here and one pair here, one of the two pairs that make up a carbon oxygen double bond is more easily pulled towards the oxygen. This makes carbon double bond very highly polar. So there's a lot of electrons here. One of the two pairs is even more easily pulled compared to the other pair, which is also pulled but not as much, and that just makes this a very polar bond. We can learn more about it here. So it's very highly polar, and the slightly positive carbon atom in the carbonyl group can be attacked by nucleophiles. Nucleophile is a is a negatively charged ion or a slightly negatively charged part of a molecule. We knew all this. And during the reaction, the carbon oxygen double bond gets broken. Nucleophilic addition. So the net effect is that the carbonyl group undergoes addition reactions, often followed by the loss of the water molecule, or the OH group. So this gives a reaction known as addition, elimination, or condensation. You'll find examples of simple addition reactions and addition elimination if you explore the aldehydes and ketones menu. Both aldehydes and ketones contain a carbonyl group. That's true. That means that their reactions are very similar in this respect. Where aldehydes and ketones differ: when an aldehyde differs from a ketone from having that hydrogen atom attached to the carbonyl group. This makes aldehydes very easy to oxidize. For example, ethanol, CH3CHO, we have a double bond with your O, and a single bond with your H, is very easily oxidized to either ethanoic acid, where you have your COOH, double bond with the CO, and the OH gets oxidized, or ethanoate ions, where you have a double bond with the CO, and the possibly what's happening here is you have your H, you have your O. Something to do with like forward bond OH, then O is slightly negative and this is slightly positive. The CO is slightly positive. So then this, so you have your O, double bond H. So then perhaps it's like go here and this goes here. I'm just making stuff up. Perhaps that could work. I mean, I'm kind of just using whatever kind of idea I have. Ketones don't have that hydrogen atom and a resistance to oxidation. They're only oxidized by powerful oxidizing agents, such as perhaps sulfuric acid, and have the ability to break carbon-carbon bonds. Which have the ability to break carbon-carbon bonds. Now, you will find the oxidation of halides, aldehydes, and ketones discussed, which is actually what we're going to be doing right now after this. So here, then we have the physical properties. We have the boiling point and the, you know, boiling point. So boiling point and reactivity. Of course, we haven't talked about the reactivity. Well, we have talked about the reactivity. We have talked about the reactivity in the sense that we've talked about the reactions, but not how easy it is to react. We've talked about reactions or how easy it is to react like this, and like this. So yeah, oxidizing agents have the ability to break carbon-carbon bonds. Okay, so now methanol is a gas. So we're talking about your aldehydes, Al, and ethanol has a very low boiling point at minus 21, and a boiling point of sorry, that's methanol. This is ethanol and has a boiling point of plus 21. This means that ethanol boils at close to room temperature. The other aldehydes, the other aldehydes and the ketones are liquids, with the boiling points rising as the molecules get bigger. The size of the boiling point is governed by the strength as usual, right? So as you go up in terms of molecule size, the boiling points get rise, so they're all going to be liquids. So let's see, van der Waals dispersion forces. Attraction gets stronger as molecule gets longer, has more MR. This increases the size of temporary dipoles. This increases the boiling point as the number of carbon atoms in the chain increases, irrespective of whether you're talking about aldehydes and ketones. Easy peasy. Van der Waals dipole-dipole interactions. Both aldehydes and ketones are polar, so that means dipole-dipole interactions are going to be talked about. Are we going to be talking about hydrogen bonds? No, we're not. Okay, we're not. They're polar because of the carbon-oxygen bond, which is a polar bond. As soon as the distribution forces, there will be attractions on the permanent dipole. This means that there will be attractions between permanent dipoles on the nearby molecules. This means that the boiling points will have higher than those of similar sized hydrocarbons, which have only dispersion forces. So when you have, you know, over here that you have an alkane, an aldehyde, and alcohol, if you have the same size, which is going to be your you're similarly sized in the sense that they have similar lengths, although not similar electrons, but similar although not identical, similar. So they tried getting as similar of the length and the amount of electrons or the MR, and they looked at the boiling point, and it says that alcohols are much stronger. Well, alcohols are the strongest, aldehydes are weaker, alkanes without an OH is the weakest because this has a hydrogen bond. This has a this not only does it have greater greater MR, I believe it should have greater MR compared to Ca, but I don't know. And it also has the dipole-dipole forces, which is the stronger one compared to your London dispersion. So notice that the aldehyde with the dipole interactions as well as the dispersion forces has a boiling point higher than a similarly sized alkane, which only had dispersion forces. However, aldehyde's boiling point isn't as high as alcohols. In alcohols, they're hydrogen bonding, as I said, as well as the two other kinds. So not only is there a hydrogen bond here, there's also O and the CH2CH3, which gives it a higher MR, and also so a greater London, and also it has a permanent dipole between the O and the H, because that's also a polar molecule. Okay. Now, although aldehydes and ketones aren't highly polar molecules, they don't have hydrogen atoms as they don't have hydrogen atoms, right? So since you have C double bond O, it's polar, but if you had if you had OH, now that's what you call polar, okay? They don't have hydrogen attached, so they cannot form hydrogen bonds. Okay, there you go. Solubility in water. The small aldehydes and ketones are freely soluble in water, but solubility falls with a chain length. As we know this for your alcohols, as the chain length increases, more will be broken, so it becomes like a worser idea in terms of energy costs to be able to be soluble in water. Anyways, let's read. So small aldehydes and ketones are freely soluble, but as they get longer, the solubility decreases. For example, methanol, ethanol, propanone. We're talking about two aldehydes and one ketone over here. The most common small aldehydes and ketones, which are stated, are miscible with water in all proportions. However, the reason that solubility, is that all the reason for the solubility is that all those aldehydes and ketones can't form hydrogen bonds with themselves. They can hydrogen bond with other water molecules. Think about it. Um, it's only a bond with it's only the intermolecular bond between an O and an H. If you have the O and not the H in the pre-existing thing, that's totally fine as long as you can find a hydrogen bond with an H. That means, see, aldehydes weren't talked. So that's also why the boiling point is it could be considered a way higher than this, because they do have a hydrogen bond. Okay, or they can form it. Yep. Well, actually, wait, hold on. Okay, aldehydes can't form hydrogen bonds with each other, but they can form hydrogen bonds with water. Because if you have CHO, let's say we just have a bunch of CHOs. Right? These can't form hydrogen bonds with each other because this hydrogen is not slightly positive, sorry. Okay, only this is slightly positive and only this is slightly negative, but the H on the other side is totally neutral, so it's going to be totally fine. It's not going to react with anything. So, but on the other hand, H2O, the hydrogens are going to be positive, so you can form hydrogen bonds with water molecules, okay, which makes it soluble for smaller molecules. One of the slightly positive hydrogen atoms in a water molecule can be sufficiently attracted to the lone pairs for aldehyde or ketone, forming a hydrogen bond. There will also be dispersion forces and dipole-dipole interactions between aldehyde, ketone, and the water molecules, because it's this, and you're gonna form like your little hydrogen, your little dispersion forces with the rest over here, and these attractions release energy, which helps the supply. However, as the tails as the chain length increases, the carbon tails get in the way of the hydrogen bonds of water, which means that they force themselves between water molecules, breaking them, which you're breaking the bonds which require energy, and you're not forming them again, because like the bonds that you're making, these hydrogen bonds, these London forces, there might be being formed, but it's just not as much as hydrogen bonds require, so it's just less energetically profitable, so solubility will decrease, so it'll just float so that it doesn't block any of the water. Okay, so that's going to be pretty much your entirety of aldehydes and ketones. Now we're looking at the oxidation of your oxidation of your alcohols using sodium potassium dichromate to form aldehydes, ketones, carboxylic acids. Okay. Alright, we're back at it. It's been a while, like a really long while, and now it's quite late, but it's okay. Now we're talking about oxidizing the different types of alcohols. Finally, getting into it. So yeah, you're gonna have. Before we start, just need to understand that we are in the absolute end of the document because I'm an idiot. We are gonna be right here. Yeah. So yeah. So we're gonna talk about alcohols being oxidized using acidified potassium or sodium dichromate solution, right? So that's gonna be your little thingy, right? And it's used to make aldehydes, ketones, carboxylic acids. You know, we're gonna leave out carboxylic acids because I feel like aldehydes and ketones are the biggest one, but let's keep them in. Now I just want to write down aldehydes. What is aldehydes? What is ketone? What is carboxylic acid? That's gonna be your COOH, right? Your double bond CO and your single bond OH, or something like that. No, it's gonna be double bond CO and OH. That's what's gonna be your thingy. This is your ketones are going to be your, your C double bond O bonded with two other alkyls, and your aldehyde is gonna be your C double bond O, the bond H bonded to your alkenes. Your alkyl group. So those are gonna be your three things that form. And yeah, you're gonna be able to distinguish between primary, secondary, tertiary alcohols using this oxidation method. So when you have different types of oxidizations of alcohols, your oxidizing agent used is going to be normally, solution of sodium potassium dichromate, as we mentioned before, acidified with dilute sulfuric acid. So again, we mentioned that it could be either phosphor or sulfuric. In this case, it'll be sulfuric, and it'll be sodium and potassium dichromate. Sodium, potassium. It could be one or either or. And if oxidation occurs, then the orange solution containing the dichromate ions is reduced to a green solution containing chromium ions. Okay. So if the reaction is successful, then the orange, so your original solution is going to be orange, which contains your dichromate. By the end of it, you're only going to have your green solution containing just chromium. Now, when I say chromate, obviously that means there's an O in it. And if I mean just chromium, that means there's only Cr in it. And there's no O, which means the O has then gone into your H to form H2O, aka water. Okay, so that's going to be your electron-Hall equation for this equation. It's going to be your C2O7 2 minus. You're supposed to know that. Your 14H plus. You're gonna have like 14 atoms of your H plus. You're gonna have total 6 electrons, and then and by the end, after balancing everything, you're gonna have 2 Cr3 pluses and 7 molecules of water. I'm not the greatest at this, but I can ignore this right now. You should already know about them, but if you should already know about them but aren't very good, you might like to have a look at this link. This is basically me. It isn't particularly important, so I will look at it soon. So now, primary alcohols, right? So when you oxidize primary alcohols, whether they can be oxidized, they can be either oxidized to either aldehydes or carboxylic acids, depending on the reaction conditions. So the reaction conditions is going to be independent variable. Dependent variable is what type, not what type, but what functional group is going to be formed. Are you going to be forming an alkane with, an aldehyde functional group, or an alkane with a carboxylic acid? So what are you going to be forming? What kind of functional group are you going to be forming? That depends on the reaction conditions, and all of this will be mattered on your primary. This is going to be a control variable in this case. Okay. Now, in the case of formation of carboxylic acid, the alcohol is first oxidized to an aldehyde. So let's say we have the conditions for carboxylic acid. Then the alcohol has first oxidized to an aldehyde, then oxidized further into the carboxylic acid. Okay, so if you want the carboxylic acid, then what's going to happen is the alcohol then first turns into the aldehyde, then it turns into the acid, and each of these is oxidations. So you can say that it further oxidizes. Okay. Now you have partial oxidation to aldehydes. Okay. You can get an aldehyde if you use an excess of alcohol and distill off the aldehyde as soon as it forms. Okay. So if you're doing the reaction and you're getting the aldehyde, okay, because you get that aldehyde first. Sorry, this is your alcohol and this is your aldehyde. Okay. So you're getting that aldehyde first. So if you distill that aldehyde and prevent it from getting distill that aldehyde before it gets oxidized, therefore you can get that aldehyde. Now the excess of the alcohol in this case a lot means that there isn't enough oxidizing agent present to carry out the second stage. Removing the aldehyde as soon as possible, as soon as it's formed, means that it doesn't hang around waiting to be oxidized anyway. So there's two things that you can do to prevent aldehyde from being oxidized. One is you want to put an excess of the alcohol so that there isn't enough oxidizing agent to carry out the second stage. Okay, what does that mean? You need, in the reaction, okay, let's say you have like this is going to be your system, and there's a controlled amount of your acid that you put in, right? Your oxidizing agent, whether it be sulfuric acid or whatever. In this case, it would be sulfuric acid if I'm not wrong. So that's going to be your oxidizing agent, and that's going to be this much. Now, the more you increase the amount of alcohols, the more it'll cause the oxidizing agents to be used up for only the first step to turn the alcohol into aldehyde, rather than the aldehyde being turned down into the carboxylic acid. I don't know why I wrote AC, it's Ca. Okay, so, and the second part, okay, is going to be just removing it as soon as possible so that it doesn't hang around waiting to be oxidized. So by the off chance it is oxidized, it doesn't, because you removed it as soon as it was made. Now if you produce ethanol as a typical primary alcohol, you would produce aldehyde ethanol. Okay, it's pretty simple to understand. Ethanol is going to be your C2H4 if I'm not wrong. So therefore you're going to have CH3CHO. So your C is going to be divided into your second one. If you start off as C2H4, that's probably going to be like CH2, right? Then, so you can write that as this. Now we aren't talking about the mechanism just yet, but then it turns into CH3CHO, which is written as this. Okay, so that's what this is. So it turns from that into this. You have one hydrogen extra over here, and you have gotten rid of one hydrogen over here, and replace that with an O. Okay. And the full equation for this reaction is fairly complicated, and you need to understand about electron half equations in order to work it out. So over here is what the half equation looks like. So we have the original alcohol, we have this, we have the amount of hydrogen atoms that we're starting with. Hydrogen atoms, of course, being from the sulfuric acid. Okay. Now you're resulting with your alcohol, your chromium itself, and your water. Okay. Now in organic chemistry, simplified versions are often used to concentrate on what's actually happening to the organic substances. To do that, oxygen from an oxidizing agent is represented as O. Therefore, that would produce the much simpler equation. So again, as we know, in organic chemistry, we would want to simplify this huge equation. Although it's simplified from the actual equation, this is the electron half equation. Although it's simplified, we would like to simplify it even more by trying to figure out, okay, what's the oxidizing agent, which is O, okay, and putting it in a box. So we can do that as we know that O is the oxidant from the oxidizing agent, and we know that it reacts with this, it reacts with the H to form H2O. So we know that O is the oxidizing agent because it oxidizes hydrogen, okay, and so as a result, we're gonna form this and this. Now notice that two Cr3 plus. Notice that 2Cr3 plus is not mentioned in both sides. It's a spectre ion almost. That's probably because you're leaving this and that's resulting in this, and you're actually gaining into this. You're actually oxidizing this. So 2Cr3 plus is not the oxidizing agent. It's going to be a reduction agent in this case because it's losing electrons. Reduction. Hold on.